go ahead and get started with our first set of speakers. We have Zach Stevens and Sarah Buffalo from WSP. And whenever you guys are ready, feel free to grab the screen and the floor is yours. Let me know if there's anything I need to do on my end to.
Great. Can you guys hear me okay?
Yeah, we can hear you.
Awesome. I'm going to try and share my screen. Unfortunately, Sarah could not join me today, so it's just me, but I think we'll be all right. And excited to talk to you about this project that we're working on with the city of Dallas. It's the K. Bailey Hutchinson Convention Center, which is a major, large existing facility, about 1 million square feet. And we've been involved at the master planning level with the city of Dallas, evaluating a bunch of new options and trying to bring a whole carbon context to the project. So that's what we're going to talk about. I didn't time this and kind of pulled it from some other presentations, so let me know if I start to go over or anything like that. And I'm happy to address questions if people have them as we go. So a little bit of context. Dallas recently, I guess middle end of 2020, issued a new comprehensive climate action plan that includes a bunch of goals for greenhouse gas emissions reductions, both for city assets and for the community at large. Some pretty aggressive targets for greenhouse gas reduction, and a target for the city itself to achieve net zero across their new construction portfolio from 2030. And they're procuring renewable energy assets across the city to compensate for that. So it's not all on site, but this project is hoping to be in line with that new goal. So the existing facility, I forget exactly what year it was constructed in, but it's been there for quite some time, and it's really just not competitive with other convention centers in the area. It's not drawing as many events or bringing in as much revenue for the city. It has been an asset for emergency responses and things like that, but even that is not quite meeting the needs of the city in the face of climate change. And as far as energy performance goes, it was performing about 57% worse than the average for a similar type facility, according to the latest 2018 CBEX data. So not quite up to snuff for the city's needs. So in addition to working on a holistic master plan with the city, which also included a bunch of other transportation, multimodal studies and community engagement and things like that, we were doing specific analysis on 4 primary options that were being considered. So you can see them at a very high massing level here. So one option is what they call the baseline patch and repair option, which would be to just kind of refurbish the existing facility, upgrade the mechanical systems to improve performance, and just kind of call it good and hope it lasts for maybe another 10 years or 30 years. It's a little hard to know. And we'll talk about how that folds into the analysis in a little bit. The second option is the campus hybrid option, which would be to largely reuse a portion of the facility and then expand to increase the amount of event spaces and exhibition halls and things like that, and also upgrade the mechanical and lighting systems and all that. The third and fourth options are new construction options. The West of Lamar option and is a larger new facility that really engages with a future train station on site. So they're adding some transit stops as part of this as well. So that was an option that was really promising for kind of opening up access to this part of the city and connecting it to nearby neighborhoods. And then they were also looking at an underground option, which was interesting. So there's kind of a little bit of the program is above grade, and then all of the large exhibition halls were below grade. So some very different options that we were considering. So the images you're looking at here are from a solar radiation study to evaluate thermal loads and also solar PV opportunities. In that same modeling software, which was Rhino Grasshopper, which we'll talk about more in a little bit, we completed a comparative daylight assessment as well. Getting into energy, we use that same software and some other plugins for energy modeling, which use basically Open Studio and Energy Plus. We were able to compare these different cases for their energy performance, as well as operational carbon. So this is a little screenshot of what that looks like in the modeling environment. So this is a really, really great tool for these early concept design studies because it's all tied to a single modeling geometry in Rhino, which is really flexible. So when you're doing those iterative massing studies with a team, it's really quick to update, and then it speaks daylight, solar radiation, energy, and as we'll talk about in a little bit, carbon. So there is each of those have individual plugins that tie to this modeling software. There's a fairly recent plugin for one-click LCA, which reads from the Grasshopper Rhino model, similar to how it operates in Revit, and you can actually produce a full whole building LCA using the same software environment. So we were excited to try this out because it allowed us to do basically 4 different types of early phase analysis using the same geometry and the same really flexible modeling environment. So it's both the Grasshopper modeling, and then you can see some of the scripting there on the right that feeds into that model, and that contains all the different plugins that we were talking about leveraging. So again, we were doing this comparative analysis and also setting out goals for the master plan. And one of the things we knew we really wanted to bring to it was this comparison of operational and embodied carbon, because there was a very obvious trade-off of performance versus new construction that we were expecting to see. So let's get into what those results look like a little bit. So in terms of total embodied carbon, based on our one-click LCA study, you can see there's a massive difference in total tons of emissions across these projects. The existing facility had mostly system upgrades and kind of refurbishment. The campus hybrid had some new structure, but also those upgrades. And then the west of Lamar and the underground facility were, several million, or between 3 and 4 million square feet of new construction. So substantial difference. Something to bear in mind here is that this is not a like-for-like comparison. The square footage and really the value that the facility adds is not the same across these because the west of Lamar and the underground are substantially larger than the existing facility. So this is looking at that embodied carbon intensity on a square footage basis, which kind of helps normalize it a little bit. But we also have to kind of think about what is the value add to the city. And one of the things we began to think about, and it's hard to quantify, but we discussed in meetings and in our master plan, is total emissions per square foot, are those the best metrics to be using when we talk about whole carbon? Do we want to start thinking about total emissions per dollars earned, the revenue that the project builds to the city as kind of a proxy for what it adds to the community, or emissions per visitor that they anticipate to see in the facility? I think we're going to get more creative and holistic with how we think about carbon emissions in these different contexts when we're comparing options. Because, if they stuck with the existing facility, they may still need 2 million square feet of programming somewhere else. And there's emissions associated with getting that value elsewhere. So these are all things we started to think about. For kind of a detailed note on the actual whole building LCA study that was completed, one thing that was not built into the one-click was the Module B emissions associated with the excavation for the underground facility compared to the excavation for the other facilities.
Hey, Zach, we're nearing the 8-minute. If you could wrap up.
Oh,
sorry.
wow, that went quick. All right, yeah, we'll keep going. So less detailed notes, but that's all good. So getting into the full results together, you can see we've kind of layered on both operational carbon and embodied carbon here. And this is over 100-year lifetime. So that was the goal for the city of Dallas. The new facility would be 100-year facility. So that begs a lot of questions about how realistic we can project into a 100-year future. Will a new construction building actually last that long? If we're trying to maintain an existing facility in the first 2 options, will they be able to continue to upgrade over 100 years, or will they eventually at year 25 have to build an all new facility? So when you think of these long-term life cycle assessments, it's very challenging to predict. And then just bringing that together, the last thing I wanted to show was depending on when you choose kind of the lifespan of the studies that you're doing, you see a very drastic difference in what becomes important. So the embodied carbon piece is much larger in a 50-year study versus a 100-year study. And again, all those assumptions that you make as a team about what future planning will have to look like based on the decisions you make has a big impact on the quantitative results of the study. So bringing that context in is really important. So for right now, they're pursuing with the West of Lamar case for a number of other reasons, including some of the, the resiliency features and community assets and the ties to the transportation planning. So we're going to continue to work on this project and make sure it achieves those goals. For net zero, working to reduce embodied carbon through smart specifications and more iterative analysis. And it's going to be a really great project for the city of Dallas.
Awesome. Thank you so much, Zach. This looks like a really cool project and a lot of really great, considerations surrounding operational and embodied carbon to consider. I think for the sake of time, I know I told the presenters that we were going to leave some questions in between or time in between for questions, but I think we'll hold those to the end. Zach, I believe there's a
Perfect.
question in the chat if you want to answer those via chat, since I know you have to drop off early, but we'll, I guess, move on to the next date in the Advent calendar. Thank you, Zach.
Yeah, thank you.
Zach, will you stop sharing, please?
All right. And so next on the agenda, we have Logan Kelley and Claire McConnell from Mithun. Take it away, guys, whenever you're ready to grab the screen.
Hey, everyone. Hey, I think Claire, please do jump in. I assume you all can hear me. Claire, please do jump in. But I think I'm going to be doing most of the talking, even though Claire has most of the brains. So let me just share my screen right now. Give me a holler if you can't see it. Should see the presentation mode. So my name is Logan. I'm an architect with Mithun. I'm based in our San Francisco office, and I'll be talking about a San Francisco affordable housing project. And specifically about the concrete, as I'm going to breeze through kind of this first grouping of slides and then kind of focus on the takeaways. So as most of you probably know, there's a lot of new municipal codes that are being generated and studied regarding the global warming potential, specifically in concrete. And different municipalities are thinking through different ways of integrating global warming potential limits on their building code. And this project that I'm speaking about was one of the test projects of the Bay Area Low Carbon Concrete Code pilot program, which was put together by this forum, as well as a few other organizations down here. And the strategy was really to take some of these codes and test them on buildings that were getting built or buildings that were in design. In our case, we had pretty much finished design and we're in the bidding process when we were tapped to try and integrate this code into our specifications. So the project was a good candidate for testing out this kind of low carbon concrete code. It's an all concrete structure building type 1. It's affordable housing, had a lot of funding sources, many of which were tax credits or local funding, some other metrics there, which I won't get into. And, I think the easiest thing to say is if you want to limit embodied carbon of concrete, you should limit the concrete itself. But it's important to remember that concrete is a super valuable tool for achieving density, mostly because you can pack 9 stories into the mid-rise height limit, which is a trick that we do quite often. So just to speak on the conventional process of specification for a second, it's linear and it doesn't provide a ton of room for analysis. And generally what I like to say is that the scope of possibility kind of decreases with time. In the very beginning, you're like, this is a concrete building. And then as you go through design, it becomes more and more specific. What kind of concrete, where the concrete's being used, where the concrete's coming from, the strength values of the concrete, the type of reinforcement, et cetera. And just to graph that, the possibility of what you can achieve with the concrete or really anything on a building, kind of plummets with time. So I think the trick here is how can you subvert that traditional process and, how can you redline that traditional process? And, I think it really starts in the beginning, no surprise there, by asking the right questions And from an architect's perspective, this kind of starts asking the right questions to your structural engineer. You know, what are the strength requirements? What pieces of concrete can we dial back the strength of? And I think a lot of structural engineers, which I'm sure there are many in the audience now, but you know, maybe not as forward thinking as yourselves, a lot of structural engineers kind of are very conservative. They specify high strength, they specify minimum cement ratios, even though the minimum cement ratio isn't necessarily directly proportional to the strength, right? So dialing in on what strength is required, what kind of performance is required, as well as making global warming potential part of the specifications and you know, divulging the global warming potential of concrete and what different mixes go into the concrete. And then, of course, another thing I think that's really important that I'll speak about a little bit more in a second is having the conversations with your concrete subcontractor and your concrete supplier. And I'll talk a little bit more about that in a second. So, you know, the goal, I think, in the end is try to keep high possibility for as long as possible. And of course, once you start pouring concrete, that's when possibility goes to zero, right? But I think actually, you know, we think about it as during bidding as, you know, where possibility is very low. You know, the project's set, maybe you get a few questions, but really low possibility for doing anything. I think what our job as architects should be is that when the bidding process is when you really start those conversations with the concrete supplier, because you know the concrete supplier, as some of you may know, they have mixes, like off-the-shelf mixes that they pull in order to meet certain strength requirements, certain pumpability requirements, certain ratio requirements. And so they're not designing a new mix for every building, right? They're using mixes that they have on their shelf. So if you're able to give the concrete supplier more leeway in using some of these new low global warming potential mixes, that really does go a long ways. And often it means writing your specs in a slightly more open format. What the process is this, a lot of these markups are from Arup, or from Frances Yang with Arup, who is a rock star, if you don't know her, who really helped us kind of look into more traditional concrete specifications and pull them apart, you know, and really, like I said before, the main thing is dialing in on what strength is necessary and trying to remove other barriers for the concrete supplier to meet, right? Strength is really all that matters. And then for the subcontractor, maybe things like pumpability and cure time, et cetera. But from a design perspective, really it's just strength. So after all of that, we did achieve a pretty big reduction in the concrete, a 36% reduction in embodied carbon of concrete on this particular project. And I'd like to just use the last couple of minutes to talk about like how to apply these lessons. The project is built. This is, you know, a photo of the project. Like I said, it's 9 stories, kind of a dense infill project in the San Francisco Mission District, affordable housing. So I think from an architect perspective, questions for your engineer. Happy to share these too, if you don't want to take a screenshot. You know, first of all, do your specs place limits on global warming potential? I think that's just you know, right away, we should be asking that question. I think the answer from a lot of engineers will be no. And, you know, understanding what kinds of tables we can introduce to the specifications to limit global warming potential, you know, that's kind of the thinking that is occurring now. Do your specs include a minimum cement ratio and why? Like, you know, again, it's kind of just a conservative thing that structural engineers have done for a long time, and understanding why that's in there and can we take it out to give the concrete supplier more flexibility. You know, do your specs require the contractor to submit EPDs? Why not, right? It's at least good for us to divulge that information and know what's going on. Do your specs include a min-max of SCMs? You know, again, looking for a min is a great way to limit embodied carbon or global warming potential. And different slabs or different concrete elements can use different kinds or different amounts of SCMs. And are your age to strength values specific to each concrete mix used? Maybe I'll transition to this slide. So, you know, on any given project, there's a lot of different elements of concrete. And there are certain elements that lend themselves to SCM replacement more. Specifically, you know, mat slabs, columns, walls, you know, these kinds of big concrete objects, whereas where they don't necessarily have to cure that quickly. Now, once you get into the slabs, oftentimes the contractor is kind of trying to build a slab once every week, once every 2 weeks. So these are the things that need to cure quickly. They have really high strength ratios. So those are the areas that may not be low-hanging fruit, and maybe you don't get higher SCM replacement or better global warming potential on those elements. And, again, the architecture is responsible for a lot of things, including what I'm talking about. And you also have to deal with the contractor being a little bit skeptical about new concrete specifications. So, things to ask from your contractor. Have you even looked at the concrete requirements on this project yet? Can we talk to the concrete subcontractor and supplier? Can they look at our drawings now? What are the kind of off-the-shelf mixes that they have? Can we look at those things? And, what issues do you anticipate? Is this a pumpable mix? Are you able to put finishes on it? Some finishes don't like SCMs very much. They're really made for high cement. So, these are the questions that you should be asking your contractor, asking your manufacturers, et cetera. And I'll just end on this slide, which again is from Francis, who I've worked with pretty closely at this point. Tips to lower carbon on every project. Set the maximum embodied carbon or cement concrete. Specify the latest cure times possible. Separate out your mix types so the supplier can pick and choose more easily. Remove prescriptive specs. Require EPDs, and connect with the construction team as early as possible. And, of course, advocate for these GWP limits. And I think I'm about at 8 minutes, so I'm going to stop sharing and happy to answer questions in the chat if you all have them.
Perfect. Thank you so much, Logan. It's really refreshing as a structural engineer to have the architect talk about concrete for once. So thank you so much. And next, just to make sure we keep on time, we have Jessie Templeton with GGLO. Go ahead and take it away whenever you can grab the screen.
All right, thank you. So today I'm going to talk about the Pathfinder tool. And this is a carbon tool that's focused primarily on landscape design. So within our office, we have architecture, landscape, and interiors, and we're doing carbon accounting on everything. The credit of this definitely goes to our landscape team, however. The case study we're going to look at is in North Seattle, and it's an affordable housing project that's really focused on families. This is the site itself, and what you probably notice is that there is a ton of open space. Essentially, there's a stream daylighting at the right side of the site, which is the south side, and there was a pretty large buffer that we could not build in. That really prompted us to think about the use of this space in a different way. Also, on the site, they're thinking there will be roughly 200 kids, which is a lot of kids. So most of the landscape design is really focused on different types of play spaces. What you see here, there's a basketball court, there's a very large play space, there are community gardens, and there's sort of a boardwalk that goes toward the natural space that's maintained at that right side of the site. The project itself is a mid-rise building. It's an E-shape that on the second floor, these 3 bigger blocks are connected, and then 4 townhouse buildings. As far as landscape carbon accounting, we're looking at embodied carbon operational, which is really maintenance in this situation, and then carbon sequestration, what plants can sequester. For this project, it's fairly typical for a lot of what we do here in Seattle. We're using wood decking, crushed stone paving, rubber play surfacing, asphalt paving, and concrete pavers. And then our planting approach is everything from lawn through larger trees and a really mixed plant palette, primarily native plants. When we ran the Pathfinder tool, we found that it was 92 years to positive. Again, this is only the landscape. So you're just looking at those exterior paving materials, et cetera, and then the sequestration. I will say that the concrete kind of didn't look quite right to me. And so I ran similar analyses with Tally and then also looked at EPDs. And currently Pathfinder is including like a 30% contingency for concrete above what Tally does. And so that's something to be aware of when you do your reviews, just that we might actually hopefully be doing better than it indicates. So looking at this, we wanted to get to positive much more quickly. We looked at the main hotspots for this. It was really the concrete, the asphalt, and rubberized play surfacing, which is one thing that surprised us. We did a lot of research looking at, what alternative materials we could use for similar applications. And I'll go through this quickly, but just noting, we found that pervious concrete would be about a 41% reduction to typical concrete, Porous asphalt, about a 60% reduction to typical asphalt. Stabilized crushed stone, a 91% reduction as compared to concrete. Natural stone pavers, a 24% reduction as compared to concrete pavers. And grid supported grass paving, about a 95% reduction as compared to paving, though the caveat is this then has to be watered and maintained. So those considerations are important. And finally, wood pavers would be about an 82% reduction to concrete pavers as well. Also looking at other low carbon on-grade material options such as mulch and wood decking, etc. Looking at the sequestration side, essentially one small tree can sequester enough carbon in a year to produce 1 kilogram of cheese, or 0.02 meters cubed of concrete. Not much. That same tree over a lifetime is essentially one flight for one person to go from LA to New York, or 1 meter cubed of concrete. So obviously our first task is to reduce the carbon. While sequestration helps, it is not the overall solution. Some factors affecting carbon sequestration rates, essentially biomass, the health of the planting, the strategy as far as diversity and layering, and the climate zone as well. And in general, the older the tree or the plant material, the more carbon it will sequester. So the larger the tree, the more mass it has to sequester carbon. It does even out over time. As far as trees of the same size, deciduous trees actually sequester more carbon than evergreen trees. But that said, especially here in places like the Northwest, evergreen trees can grow really, really tall. So if you have room for those on your site, those can be an excellent means of carbon sequestration. Plant materials such as bamboo that are really quick growing sequester more carbon early on, but native species tend to sequester carbon for longer. And then the more diverse our planting layers, the more diverse our soil is and the more carbon storage we can acquire. As far as operational carbon, we're really encouraging our owners to switch over to non-gas powered maintenance equipment and no pesticides or fertilizers, which is something that we already mandate. So if we look at our baseline, again, we have asphalt paving in the driveway, we have concrete paving on sidewalks, we have concrete seat walls, there's some metal work, we have metal play structures, and we have the rubber playground. So we looked at this and said, how can we revise this to a low carbon solution? We used wood furniture instead of concrete furniture, wood play chips instead of the rubberized play surface, wood play structure instead of the metal play structure, grid supported stabilized crushed rock instead of concrete, layered planting to increase biomass, and also more trees. And this got us to 0. Actually, did not. It got us to 32 years to positive. So obviously there is more room to grow and revise, but this is where we are right now. And we've used this on a few projects so far and are still trying to figure out, what our typical is as far as years to positive for what types of projects. And with that, I will turn it back over to you all.
Awesome. Thank you so much, Jessie. Really interesting to see the landscape side of things in this discussion. So next, we have Joe Mayo from Mahlum, and we also have Jessie Walton from Mahlum. Feel free to grab the screen whenever you're ready.
You'll see my Alki in lights here. Yeah.
Good
So
to
Joe
go.
and I are going to share, oh no, my presentation mode went to my other screen. Oh well, I'll just use it here. Joe and I are going to share where we're at with Alki Elementary School and its embodied carbon reduction goals. It's a Seattle Public School project. And I just want to shout out the team real quick, PCS, especially PCS Structural Solutions and Cornerstone General Contractor for helping us reduce our embodied carbon on this project. Quick overview of the project. It is in West Seattle. It is right just a couple blocks south of Alki Beach. Here on the left, Alki Park's adjacent to it. And it's a new school, 82,000 square feet total with the existing gymnasium in orange here. And it's 3 stories. As far as orienting you to the plans, you can see at the main entry is right off the park with the public dining common space, the existing gym off to the east, some kindergarten classrooms, and then the second and third stories really stack 100%. The only exception is the art and the library, which are kind of wrapped around this central atrium. You get one pretty picture. I think the rest is going to be numbers. This is that main entry coming off the park, and you can see all the mass timber exposed, and the lateral system is in steel. So now jumping back to where we started about a year ago in the schematic design, we had an eco charrette with the client, Seattle Public Schools, who already has a lot of really strong embodied carbon goals, one of them being a 20% reduction in embodied carbon. And when we did our EPIC model and walked them through all the carbon reduction strategies for embodied carbon, we said really the only way to assure that 20% reduction is to change your primary structural system to mass timber. In that moment, somebody said, we're not scared of mass timber. We are already working on a 2-story mass timber school in the district right now. I think it was still in design, about to start construction. And so we proceeded from there to work with the contractor and the client on this 3-story project.
And as a little bit of history, we had been looking since 2019, we started this Forest Wood Innovation Grant study looking at a 3-story school and taking a typical structural bay. You can see here the steel and concrete versus mass timber and gypcrete, and doing some analysis and tally to see what the impact would be in terms of embodied carbon, and finding with the inclusion of biogenic carbon, really a kind of night and day picture between the embodied emissions. And if you go to the next slide, Jessie. So as we started out the process back in SD, Cornerstone, our general contractor, came on board. PCS, our structural engineer, we had been kind of scheming around mass timber. We wanted to make sure the entire team was on board. So we had a specific mass timber workshop to kind of align everyone's intentions and ideas about this, and identify pros and cons with the mass timber versus some other structural options. And then after going through that, identifying the challenges and things we needed to do additional research on. And so as SD closed, we sort of went through those and identified possible solutions. And so PCS, we had been working with them already during SD to kind of figure out what the most fiber optimized design would be in mass timber, trying to utilize as little wood as we possibly could for the primary structure, starting with a 30 by 30 bay, and then looking at ways to reduce that amount of fiber. And these are some of the early studies that we did before. Yeah, if you go to the next slide. We landed on really a system several of you have probably seen before, but we have about a 11-foot span in the north-south direction, no columns or no beams running north-south. All the beams run east-west, and then a 28-foot span, so 11 by 28. And then in blue, you can see the steel and brace frames. And in the middle there, wanting to bring daylight in, we were really hemmed in by the incredibly small lot size. So we had to pretty much fill up the lot to get the program that we needed there, and within the height limits. And so creating really a zipper down the middle of the building, which had some additional structural implications and some fun with mass timber.
So that was a really quick year-long process from schematic design to now construction documents. Now we find ourselves in this place where we have a much more detailed Revit model where the client is 100% the contractor, 100% bought off on doing this mass timber school. So we're now testing our assumptions from schematic design using that EPIC tool with our tally model. The EPIC tool told us we were going to have somewhere around 480 kilograms of CO2e per metered square for the global warming potential. Right now, tally is telling us we're somewhere in the low 200s, which is aligning well with the CLF benchmark, the 2017 benchmark. You can see they're in the low 200s kilograms of CO2e per metered square for that benchmark. I realize there's some different things that EPIC and tally are modeling, so it's probably not apples to apples in this case. But we've also started to dive into the details and really try to make sure our Revit model and our tally model is accurate. So we've developed this Tableau dashboard. If I can share real quick. It's basically, I mean, we've only been using this, I want to say, for a month on this Alki project. We haven't been using it on all the projects in the office yet, but it's really allowed us to look at each material, each life cycle stage in a visual way. You can see everything in blue here is global warming potential. On the left here, it's kind of like a tree map stacked bar chart that's organized by life cycle stage, spec division, and material category. And the material name is here on the right, and they all act as filters to one another with these key performance indicators, including the total global warming potential, the total social cost of carbon based off of a $50-ish per metric ton. And then I included this really kind of a visceral metric, the mortality cost of carbon, like how much additional deaths is this project causing. Haven't shared this one with the client yet, but I think it's an interesting way to see this internally. So you can see here, if you look at your end of life, you can see the vast majority of the end of life carbon is coming from the wood, and inversely in the A1 through A3 life cycle stage, the vast majority of the biogenic carbon is coming from wood. We've also used this to just QC the model. This is the most up-to-date version, but originally this finishes section was probably more than half of the global warming potential, and we realized that something was wrong. So we were able to dive in and figure out that it was our flooring. Our flooring actually was just being calculated incorrectly. The way it was modeled, the way the EPD was entered into tally model. So it's been, I would say in the month we've been using it, a pretty interesting tool to utilize and understand our tally models in a more visual way. I think that's it.
Yeah, perfect. Thank you so much, guys. Love seeing that mortality cost of carbon. Very interesting stuff. So the very last presenter we have is Adam Slivers from Holmes. And Adam, feel free to grab that screen whenever you're ready to go. Floor is yours.
Thank you. Okay, how's that look?
Cool. Got it.
Okay, so this project was from a number of years ago when I was working at Lund Uppsala. This is a design build project with HOK and the Walsh Group at the SeaTac Airport. And thanks to HOK for the professional photos. Also, it's amazing to see what construction photos I still have on my phone. It is a 32,000 square foot steel frame building at the airport. It's the white roofed structure that you see as you approach the departures drive. It's a 6-gate terminal for buses departing passengers to board planes at the tarmac, or the hard stand as they call it. We pursued this as a steel frame building, and we had a steel truss as the baseline when we went into the final proposal. Just after award, and I'll walk through the time frame for this project because I think that's the most notable part of it. After award, we realized that the trusses that extend over the top of the building were creating thermal bridging that wasn't meeting our energy code limits. And so we switched to timber trusses at the roof. This project was LEED version 4, the first one at SeaTac Airport, and the contract goal was LEED Silver. It was actually the first LEED airport terminal building in the US. The airport has district heating using steam, and that had to be used. So also they have a master site plan that's a LEED rating system on its own. And so we had a lot of those credits fixed. So when we did the LEED checklist, and I'll talk about the timeline of that, it was 50 credits in the yes category, and that's the minimum threshold for silver. We had 7 credits in the maybe category, and so that meant little room for error. So I'll talk about the time frame. You can see the plan for this project is just basically a single story structure with a small mezzanine. and the connection to the rest of the Concourse D terminal. So we fulfilled the request for proposal starting in December of 2016. We submitted our design build proposal in February. We were awarded in March. And all the way through the end, substantial completion is about 18 months. So, you know, we went to building permit from March to July, and then we went to construction documents by November. So what happened in the middle there is we did our lead checklist in August. That was just after we had submitted for permits. So we had the structure designed. And that was after we had switched to wood trusses back in May through that thermal issue. But then in November, the owner rejected one of our lead point credits. Actually, it's 3 credits for low flow urinals. And the reason, and it was just no fault to either party here. It was literally just misinterpretation of the specifications of their fixtures. We felt that we could provide the low flow value, but they have clearly had maintenance issues in the past for those. And so they really pushed back on that. So it's a pretty dramatic point in the design just before we were going to construction. And then so we actually executed the whole building LCA effort on this project after we issued construction documents, while we were checking concrete submittals and while they were grading the site. We submitted the lead documentation in December. So we effectively completed the whole building LCA in a month. And my portion of the work was, you know, HOK was saying, hey, we did a timber roof. Can we go back and say like the steel roof was X and the timber roof is Y? And I was like, yeah, absolutely. But I felt that that wasn't clearly going to be enough. And I just talked to the concrete foreman and said, what's the lowest concrete cement content you can comfortably accept? Can we do a high cement replacement on this project? And he said, yeah, I have some experience with Cal Portland's 50% slag mix on my previous project, and so I'm okay with that. And I talked to Cal Portland and I talked to them about those limitations, any potential things, and we were on our way. Switched the mix after we had approved it the first time. This was the steel and timber going up in March of the following year. We did have cold weather concrete. We had freezing weather right when they were preparing the forms for the foundations. The initial mix was a 6-act Portland cement for the foundations and 20% replacement for walls and slabs. That was our initial goal. Is I think we had 17% cement replacement as our baseline. That was what we had accepted prior to the whole building LCA. And then once we replaced to the 50%, we were able to get, like, for the structure alone, about 30% reduction in all of our whole building LCA limits, environmental outputs. And then I knew that they, you know, HOK had to come through with the curtain wall on the roof and calculate the whole building to figure out where we were in the goal. Obviously for lead V4, this before they changed it in 4.1 was you had to get 10% reduction in I believe 3 of the 6 categories. And we actually had 10 to 15% reduction in 5 of the 6 impact categories. We had polished concrete on this project, a lot of carpeting in the waiting areas, but polished concrete. And I just recently talked to the concrete foreman for Walsh Group, Steve Santos, and he said, you know, the finishers had a little heartache, but you know, it'd been nice if we had some flash in there or something to kind of create a little bit more fluid in the mix, because slag can be sticky. But overall, it was pretty successful, and the beam or the column pockets, you know, having those slabs poured later after the foundation was cast, and it allowed the steel to go up without any limitation on the concrete pouring and the set time. So anyway, we had a great finish. The project looks beautiful. The wood trusses are, you know, definitely a highlight in the building. Polished concrete floors look great. And we successfully opened the project in September of the following year. So that's my presentation, and thanks to HOK for these great pictures. Now, since I've come to Holmes, fast forward about 4 or 5 years later, we're now, not talking about cement replacement anymore. We're talking about greenhouse gas limits. So we now have in our general notes for all of our projects in Holmes US, the embodied carbon limits or cement limits on our general notes. And we just went in for permit on the storm practice facility here in Seattle, where we successfully executed that. And actually our limits are a little bit more aggressive, just to the design intent of the project. Our standard limits are readily achievable in all of our regions. So we're pretty happy to have that as kind of the new approach to embodied carbon. That's all.
Fantastic. Thank you so much, Adam. I know I was in the airport just a week ago and accidentally stumbled into that area and was pleasantly surprised by all of the mass timber. Thanks for giving us some insight. So I guess now we have some time left for questions. I think we can, if there's anyone in the audience right now that has anything to ask, I think there's a couple in the chat. Okay, we'll go to the chat. So first one, Adam, we'll start with you. What whole building LCA tool were you using in 2017?
Yeah, so we actually did a back of the envelope with Athena because it was free and readily downloadable. I actually spent only, maybe 2-3 hours at that point. We had the volumes of concrete from Walsh VDC, and the rebar was, already quantified for the concrete. When we handed that off to the to HOK, they used Tally for the final design, and we checked their numbers and validated that effort.
Gotcha. Sweet. And we'll go for the Alki Elementary case study. Do the mass timber floor assemblies have a concrete slab? If so, how does that assembly come apart or not at the project end of life? And what were the CO2 emission assumptions in life cycle phase D?
No concrete topping slab for that, just looking at acoustic mat and gypcrete topping. So supposedly floating topping. So at the end of life, I would imagine you could pull that stuff off and still have your CLT without a whole bunch of screws or anything going back down into it. So hopefully facilitate reuse. And I know that kind of floor assembly has been vexing for me for a long time in Tally. We're just using the standard cementitious topping that's in Tally, and I think we're using like a SBS rubber mat, which looking at a EPD I had for an acoustic mat, it was around the same GWP. So we think that I don't know, hopefully the numbers are fairly conservative there. And I'm not haven't really dived into what happens at module D for those particular elements. I think the rubber mat probably could be, I think it's from recycled material. I don't know if it could be recycled again. And then the gypcrete, I don't know what if there's any benefit to that beyond the system boundary for module D. If anyone else knows, that would be love to hear.
Yeah, we haven't really gotten into the part where we've started deconstructing mass timber buildings that often, so it'll be interesting to see that later down the line. Let's see, looks like we have one last question, and if for anyone who hasn't been monitoring the chat, there's some really great answers too that Jessie's been providing on her presentation as well, but those have already been answered, so I urge you to take a look. We've got one last one for Adam, and I think we'll wrap up after this. But Adam, have you found that subs are increasing the price for concrete mixes now that you have specified max GWP limits?
No, because the max GWP limits are, I'd say we played around with this number, but they're somewhere between 70 and 80 percentile in terms of you know, what you can achieve if you looked at them in the EC3. And really, it's just the need to get those on the drawings and having them, all of our engineers like get these questions like, hey, what's this? You know, hey, why is this a limit? And it opens the conversation. We certainly have, you know, our green projects push that, you know, drop it 10, 20% pretty easily without even, you know, getting to the point where talking to the concrete supplier and seeing availability and price changes are an issue. So I'd advise like everyone to realize like the low hanging fruit in reducing cement and in concrete construction is generally cost neutral. It's worth a conversation, you know, if finishers say that there's going to be a cost change, you know, ask those questions, you know, inquire why, but you know, we can only learn by doing.
Thanks, Adam. So let's see, I think that's probably a good time to cut it off here. Want to thank everyone so much. Thank you, Zach, Logan, Jessie, Joe, and Adam for the time you spent today sharing your case studies. It's been incredibly enlightening to see all of the work that you guys have been doing. We've got a lot of good stuff getting ready for the new year, and really excited to see what happens in 2023.